Our transactions currently create the relevant output objects to send currency from one individual to another. However, we still have to create the vital input object, which provides information about the sender. This information includes the sender's original balance, his or her public key, and most importantly, his or her signature for the transaction. To generate signatures, our elliptic module gives us a convenient method called sign within the key pair object. This allows us to take any data in its hash form and return a signature based on the key pair, private key, and the data. Later on, this generated signature and the matching public key can be used to verify the authenticity of the signature. Let's add this signing feature to our wallet class with a new method called sign. Sign will take one parameter, which is a data hash. In other words, the hash representation of some data. As a result of this method, let's return a call to the sign method contained in the keyPair object of this wallet class. So return this.keyPair.sign, and then the input for the sign method within the keyPair object is the data hash that we're signing and generating a signature for. So overall, that's return this.keyPair.sign data hash. Now we can create our method, which creates the input objects for a transaction now that we have a way to generate signatures based off of the wallet. Since the effect of creating an input object includes generating a signature for the transaction data, let's create a sign transaction method which is devoted to generating this input object within transaction.js. So after new transaction, we're going to have another static function, and in this case, it's called sign transaction. This sign transaction method will take two parameters: the transaction object to create the input for, so let's have a transaction input, and then also the sender wallet, which will have the balance and the public key, and also the signing ability to generate the signature. In this method, let's assign a value to the input object for the transaction, meaning we're going to take the input and then assign it to an object. Each input will have a timestamp field, and the timestamp will be date.now, which returns the number of milliseconds which have actually passed since January 1st, 1970. So the higher that number is, the more recent the timestamp. And then we're going to have amount, which is the sender wallet's balance, so sender wallet.balance. We'll also have the address, which is the public key of the sender wallet. So public key. And then finally, there is the signature field for the input. The signature will be generated by calling the sign method within the sender's wallet. And what do we want to sign? Well, we want to generate a signature for the entire transaction itself, but it doesn't really make sense to sign the whole transaction object since we're still creating the input object for this. But we can sign a large majority of the data by signing the transaction outputs. So we'll use senderWallet.sign, and then the actual data to sign will be the transaction.outputs. Now, there's one more thing. Recall that the sign method expects the data to be in the hash form. After all, it's much more efficient to have a hash value with a fixed number of characters to sign, rather than a potentially large object that could be full of long pieces of data nested somewhere into that object. Luckily, we have a hash function that is already being used to generate hashes for blocks within our blockchain block.js file. So let's take advantage of that function and then stick it into the chain util class so that way we can also use it within this transaction file. So first, let's head to block.js. So let's go to block.js within the blockchain. Let's cut the declaration of the SHA-256 function right at the top. And then we're going to stick it into our chain util file. So right after our const EC, we're going to also have our SHA-256 requirement over here as well. Then we'll declare a static hash function within here that takes an arbitrary piece of data, stringifies it, passes it into this SHA-256 function, and then returns the result. So again, we're going to have our static hash function. It'll take data as the parameter, and then it will return the SHA-256 function. So it'll call SHA-256. It will stringify the incoming data, and then it'll toString that form, and this will generate a hash of whatever data comes in, no matter its form, whether that's a string, a number, or an entire JavaScript object. All right, great. Since we've removed the SHA-256 function from the block class, well, let's use this hash one within the chain-util class instead within block.js. So first up, let's replace that dependency with the chain-util dependency within block.js. So now we're going to acquire the chain-util class and require it by going up one directory to /chain-util, since the block class is one directory above the chain-util file. All right, and now our static hash function, rather than calling SHA-256 directly, we'll call chain-util.hash. Great. Now we can do the same thing in the transaction class to create a hash for the transaction outputs, which we're using to generate the signature. So in transaction.js, well, make sure that you have chain-util right at the top. And then for the transaction outputs, we can wrap around chain-util.hash to create a hash of the outputs before the signature is generated with the sender wallet's sign method. Excellent. That wraps up the sign transaction function. Lastly, we'll make sure to generate an input by using this function whenever a new transaction is created. So we'll call sign transaction in the new transaction function after the outputs are created. So we'll use it in a static way. We'll say transaction.signTransaction, and then the inputs are the current transaction object that is being created, and then the sender wallet that is also passed in to the new transaction itself. Perfect. That wraps up signing transactions and creating an input object with a signature. Next, let's add a test that asserts that this input object actually exists when a new transaction is created. Then, because we've now generated signatures for the transaction, we'll follow up with methods that verify the authenticity of that signature.